Welcome to the Week 1, Section 2 course material. I'm going to walk through a couple of key things that we need to know before we start programming. So some of the key concepts we're looking to cover is what is a computer system in general, what is hardware, what is software, what are some common terminologies in software development, a little bit of a history on programming languages, and why we care about C#, which is a programming language that we're going to use for this course. In the upcoming lecture, we would be talking about the software development lifecycle, the SDLC. We would talk about Agile Scrum process. I'll introduce you to Visual Studio. And it would be a good idea if you start by reading Chapter 1 before the next lecture. All right, so let's dive right in. So what is a computer system? The computer system is any type of system that has some form of software and hardware, right? So in general, a computer system would have software and hardware. And you might be asking yourself, well, what is hardware and what is software? So in general, when a user interacts with a computer system, they typically would have some type of hardware device, some physical device that they can touch, say the monitor, the keyboard, the mouse, and other components of a computer system, right? That hardware or physical device would have some type of software installed on it, software being some programs. Now those programs can be divided into two major categories. The typical programs that a user is interacting with, say Microsoft Word, Microsoft Excel, PowerPoint, websites, so on and so forth, could be thought of as applications. Now it's important to note that when we say something is an application is not just a mobile app. Applications could be mobile applications, mobile apps. We could have web apps. We can have console applications, and so on and so forth. And we'll dive a little bit deeper into some of these. You can have games. All those are applications, right? Operating systems, on the other hand, would be the underlying software on top of which these apps are installed. So think of the definition of a computer system, and if we were to think about it in terms of mobile phones or cell phones these days, a mobile phone has some type of hardware, and then it has some type of operating system, and then you can go to the App Store and install apps on it. Now your typical desktop machine, or PC if you will, has some type of hardware. It has an operating system, and you can install different applications on it, or it can access different applications, right? So as an end user, you're interacting with apps. Apps sit on top of an operating system. An operating system is installed on a hardware, and typically when you buy a device, most devices would come with some type of operating system already installed on them, right? Just try to think about some examples of mobile phones and how these categories of things fall into this. So let's say the Apple iPhone, right? Apple likes to put I in front of just about anything, so iPhone is Apple's mobile phone product. So that device could be, iPhone X is the actual hardware that you're probably purchasing. And it comes with an operating system already installed on it, typically iOS, right? So the little I for Apple, OS is short for operating system, if you will. So that device, physical device, hardware, has an operating system called iOS. And by the way, you can install apps on it, right? It comes with some apps already installed on the operating system. For example, you might have the Photos app, maybe a calendar app, so on and so forth, right? That's the breakdown of that. Now think of another type of phone that is not an iPhone. Maybe we're talking something in with Android, right? So it might be the Samsung phone, right? And it has some type of operating system, typically Android. So Android is an operating system, as iOS is an operating system. And you could still have the Photos app on that phone, right? And maybe a calendar app, so on and so forth. All kinds of apps you can install on there, right? So that Samsung phone, the iPhone, they are all physical hardware devices. They would come with some type of operating system already installed on them, and then you can install different applications on that. Now the desktop would have, if you buy a Mac, let's say an iMac as a desktop machine, it will come with some type of operating system, typically called Mac OS, right? So that's the operating system for a Mac machine. And then on there would be, I have PowerPoint running on this machine, this Mac laptop that I'm using, right? So PowerPoint is an app that runs on top of this. I have Google Chrome, so on and so forth. If I had a desktop, maybe it's an HP laptop of some sort. So the actual hardware is some HP hardware, but I have Windows 10 installed on it. That's the operating system, right? The OS on there. And then I might still be able to install PowerPoint on there. I might have Microsoft Word, so on and so forth. So that kind of gives you an idea of what apps are versus operating systems. And now let's dive into the next slide. So now we're looking to talk a little bit more about hardware versus software. So hardware could be categorized as the physical components of a computer, and there are multiple components, hardware components in a computer system. Some notable components that we care about before we start learning how to program would be CPU, the central processing unit, right? So CPU is the brain of a computer system. Think of the CPU as the brain of the computer system. Just like a human, we process different things, information, using our brain. When the computer system is processing data or instructions or program code, it will use its CPU to do that, right? So this CPU here would be running most of the programs that we're going to be writing, right? Another name for CPU is processor, right? So the processor is who is doing all the work in a computer system. Now, something else of note is random access memory, right? RAM. So random access memory is sometimes referred to as primary memory, also referred to as temporary storage. It's nice to know some of these synonyms so you can relate to these if you're reading different textbooks and different materials. It's practically the same thing. Random access memory, primary memory, main memory, temporary storage, same concept. It's important to note that computers process data behind the scenes using zeros and ones. And we like to call the number system that consists of only zeros and ones as binary, right? So binary has only zeros and ones. Behind the scenes, the computer system only knows zeros and ones. It's like flipping on a switch the on state of the switch is 1, and the off state is 0, right? So if we wanted to represent the number, let's say the number 1 in binary, it might be represented in a form similar to 0, 0, 0, 4 there. The number 2 in binary would be represented by something like 0, 0, 1, 0, right? And then the next number 3 would be represented by something like 0, 0, 1, 1. Essentially, we're looking for the first number with only zeros and ones. So we've got, 4 little bits, I should say. And it's important to note that 0 or 1 would be referred to as a bit, B-I-T, right? And 8 bits make up 1 byte, right? So in measuring how big your memory is or how big your hard drive is, we would typically speak about that in the order of gigabytes. So we might say you have 4 gigabytes of memory, 8 gigabytes, 16 gigabytes, so on and so forth, right? But that boils down to, behind the scenes, there are 8 bits, right? And so technically I'm only representing this in terms of 4 bits. If you had 4 leading zeros in front of this, these would be in bytes. So the byte representation of the number 1 in decimal form that we typically count in would look something much like this in binary form in terms of bytes, right? So we have 8 bits. This is in 8 bits. The number 1 is this. The character A would have its own representation, B, C, so on and so forth. Think of an image or a video. Anytime you record something like that and store it in the computer system and you need to process it, that needs to be converted into zeros and ones, a series of zeros and 1 binary numbers before the CPU can actually process that, right? So in general, you're going to be loading data from your secondary storage, and secondary storage is much like your hard drive, your USB flash drive, your C drive, as you probably know it, or your D drive, so on and so forth, right? Those are the terms in which we're typically used to thinking of secondary storage. So it is some permanent storage. I'm going to move that here and put my notes down here for you. So secondary storage examples, we said our hard drive, USB flash drive, right, so on and so forth. SSDs, solid state drives, right, so on and so forth. These are permanent storage devices. So imagine you're typing something in Microsoft Word and you haven't clicked the save button yet. Everything you're doing at that moment is in temporary memory, which is RAM. As soon as you click save, you're actually saving to some location on the computer, right? Not some virtual location. You're going to specify that I'm saving to the C drive or the D drive or my documents folder, some specific folder on the computer system or an external drive, and that would be secondary storage. Now the difference between secondary storage and RAM, RAM is typically more expensive, right? But it is significantly faster. Okay, so if you can get your programs to run in RAM or memory, they're going to be significantly faster. Secondary storage is on the opposite end, a little bit slower, but cheaper, right? So in most cases, you might have a lot more secondary storage than you have random access memory. So your hard drive might have something in the order of maybe 500 gigabytes, right? And this GB is gigabytes. Giga meaning 1,000 bytes, so 500 gigabytes. And we said 8 bits make up a byte. So we're talking in terms of how many of these zeros and ones can I store on my computer system, on my hard drive, right? So you might have 500 gigabytes. You might have maybe you have 1 terabyte of data, right? So on and so forth. Whereas your RAM is more likely to be something in the order of maybe 4 gigabytes, 8 gigabytes, maybe 16 gigabytes, so on and so forth. I'm going to show you on my Mac how I would identify how much RAM and CPU I have. So on the Mac, if you clicked on your Mac, your Apple logo, and went to About This Mac, you should see a pop-up that looks something similar to this, right? And right on here it says I have 2.5 gigahertz with an i7 Intel Core processor on my Mac, right? So that's how fast this CPU is, 2.5 gigahertz, and it's on i7. I have 16 gigabytes of memory, right? This is actually pretty fast. Most Macs would probably be around 8 or 4 gigabytes. My graphics card has some capacity, so on and so forth. But for the sake of this conversation, we're talking more about the processor. We said processor is synonymous with CPU, central processing unit. If I needed to figure out how much storage I have, which is secondary storage, right? I could flip to this guy, and it tells me I've used 120 something gigabytes, or I have that much available out of the 500 gigabytes. So this machine only has 500 gigabytes of flash storage or secondary storage, right? I only have 500 gigabytes of it, but I do have 16 gigabytes of memory. So every program that I run on this computer actually ends up getting loaded into memory. It's going to start off in secondary storage. Then it gets loaded into memory. Once it's in memory, if the program has a couple of instructions that would be executed using the CPU, right? All right, so next slide. Software, on the other hand, we spoke quite a bit about that. We said it's the programs that run on the computer, operating system, some examples, Windows, Mac. I'll give you some other examples as we're not in class. Linux and Unix are some very good examples. Chrome OS, also very good examples of operating systems. Obviously, iOS, Android, so on and so forth, right? Application software is up to your imagination. Anything that is not an operating system and it's a program that runs on a computer is an application software. So here's a good example of a number of apps versus iOS screenshots, just to jog your mind. If you are looking at this is more than likely a Linux operating system of some sort with the desktop showing. This is more than likely Chrome OS. If you've never seen a Chrome OS desktop, it looks something more like this. Chrome from Google, obviously. SAP is an ERP solution. It's an application. This is ADP. This is Microsoft Outlook. Those are just applications that would run on some type of operating system. Terminologies and the history of C#. So let's talk about C#, why we care about C#, compilers, so on and so forth. So in general, people who build software or write programs are called developers, or sometimes we like to call them software engineers or software developers. In general, we don't like to be called coders. That's kind of old school. We like to be called software engineers in most cases, or software developers or application developers. Sometimes we like to call developers hackers. That is because in some cases, when you're learning how to build programs or build things, you might not necessarily have a full grasp of all the components. You don't really know everything that you need to know to build it. So you might do some type of hacking by pulling content together from different sources. Maybe you watch a short tutorial on YouTube on how to build a login screen, and then you implement that, right? And then you come back the next day and you figure out, hey, I need to be able to get this application to send an email. How do I do that? So you go Google it or go on YouTube and find, how do I send emails from an iOS app? And you find a nice tutorial on how to do that. And you incorporate that. And you're learning as you're doing it, but you're not learning all of the theories behind it before you start programming. So you could think of that as hacking together a solution. And so software developers, really good software developers, are very good at searching for information, learning very quickly, and applying their knowledge to solve a problem. And that's why you get that terminology of hackers. You would hear the terminology of hackathons. So when developers get together to put together apps very quickly, obviously we don't have enough time to be learning the details of what we're doing, but we're hacking things together, right, using the same concept that I described. What's a programming language? So a programming language is some type of formal language that has precise instructions to a computer, to a computer program, if you will. So think of Java, C#, C++, Python, PHP as all programming languages. We typically do not like to think of HTML as a programming language. HTML is not a programming language because HTML is hypertext markup language. It's more of a markup. It's not a programming language, right? So if you see that on a quiz, you should be able to identify that. Some examples of really relevant programming languages would be Java, C#, Python, as you saw, PHP, even JavaScript, the Go programming language, so on and so forth, right? So here's a nice code snippet. I don't expect you to know anything about this yet, but it's interesting sometimes to try to look at this and try to see if you could guess what this code is doing. Because if you can, then you're halfway through the semester in this class. Because it's going to take us a while to figure out what are variables, how do we make calculations, how do we assign different values to variables, how do we build decisions in code with if statements and so on and so forth. And that's what this is doing. So in this code base, what is actually happening is we're creating some type of a variable. It's some type of container, and it's an integer data type. So int, short for integer, and that container is going to be called x, right? And we're going to put the number 3 inside of that container. Don't worry too much about the semicolons and all that. We'll talk about that later. And then we're creating another bucket or container called y. It's also an integer, and we're going to assign the number 5 to that bucket. So equal to means assign. So assign 5 to y. Notice we're reading kind of backwards, right? Assign 3 to x, assign 5 to y. And then we're creating another container to hold the results, and that container is called max. Max for maximum, right? Then we have some white space here. It means it has no significance. It's just to make it a little bit more legible so we can read this a little bit easier, right? And then we have another statement on this line. Now notice we're telling the computer precisely what we want it to do. And the code runs from top to bottom, meaning that if I want to assign the number 3 to x first, well, that would be the first line. If I want to assign 5 to y first, well, that would be the next line. Or however way I want this program to run, it's going to start running this line first, that line, that line, that line. It's not going to be able to read the whole thing and then process it. It's going to execute these lines in sequence. So the sequence or logic or order in which this is laid out is very critical when we start writing code. In any case, forget about all the curly braces and the parentheses for now, and look at this statement. If x is greater than y, x at the moment is 3, y is 5. So this is in memory, right? So we talked about memory. Why did we have to talk about memory? Because variables are going to be storing data in memory. So this container isn't a physical container. It's just a place in memory, in the random access memory, where we're storing the number 3 in x. We're storing the number 5 in y. So in memory, the computer knows at this point x is 3. So I'm really trying to compare 3 greater than 5. So we're saying if 3 is greater than 5, then assign the current value of x to the container named max. The current value of x is 3. But 3 is not greater than y. So max is not going to have this assignment. So the next statement says else, meaning if none of this is true, if this condition is not true, otherwise, else means otherwise, otherwise assign max y to max. Y is 5. So since 3 is not greater than 5, max would be equal to 5. So coming out of this block of code, max is going to have a new value, which will be 5. Now, you don't have to understand any of this. This is just to help you kind of think about how we need to structure computer instructions so that computer knows exactly how to execute this step by step, right? If, on the other hand, this makes a lot of sense to you, then you're really going to enjoy this class, right? All right, let's talk about the history of C#. So way back when, in 1969, C was invented by Bell Labs. Then came C++ and Objective-C. Sun Microsystems came up with Java. Microsoft came up with VB.NET and C#. C# has evolved, and over time, I believe we have C# 8 at the moment. So C# is evolving pretty quickly. There are several programming paradigms out there. I'm not going to spend too much time on this, but it's nice to know that there are multiple programming language types or paradigms, if you will. And these have evolved over the years. So there's object-oriented programming and event-driven programming. Out of the rest of these, that's practically what we're going to focus on. So we've got some imperative, declarative, procedural, parallel processing languages. We're going to focus on our efforts on object-oriented programming concepts and event-driven programming. And here are some of the buckets that these would fall into. So object-oriented programming languages, kind of the popular languages you and I know of. You've got procedural languages like COBOL, Fortran, BASIC. Those are languages I had to learn when I was in college. No longer relevant these days. Let's get back to the CPU, because this is actually the reason why we were talking about CPUs. CPU is a central processing unit. We also said it was the processor. So it's the piece of the computer that executes the program instructions. When we write code, this is the guy who is actually going to work with that. And it only understands zeros and ones, not the typical English programming languages that we're going to be using, right? So the binary digits represent the smallest unit of data storage in a computer system. So we need to convert this English code into something that the CPU can actually understand, because it doesn't know what we mean. To do that, we need something to do the translation of the code to binary. Remember, binary is zeros and ones, right? And you can try to reflect on some of the things that we talked about. What's a bit? How many bits make up a byte? Which of the two binary digits represents the on state? Those are things we covered. You could always go back, replay the video, and get those answers. A compiler is responsible for converting the English code that we're writing into the zeros and ones that the processor needs to get the computer to run the program the way we need it to. So we're going to write some code in English. There is going to be a program on the computer system called a compiler. It's going to translate our program code into some binary code so the processor can actually process that. And this is kind of the .NET platform. So the .NET platform allows us to take some of the C# code source files that we write, a bunch of images and resources and things like that, compile them into an executable. Sometimes we like to call this an assembly, right? An assembly, which would be a .exe is an executable, or DLL, a dynamic link library file. Both of those are referred to as assemblies. Then get them down to something that could be processed by the .NET framework and then eventually into machine code. So the native machine code that the operating system is going to be working with at that point. Another concept that we should be aware of is the idea of an IDE. So an IDE is an integrated development environment. It's basically a program that's used to build programs, right? So for us to build programs using C#, the programming language, we're going to be using Visual Studio, right? So Visual Studio, you need to download Visual Studio. Visual Studio is going to be the tool that we use to build C# programs, right? Now, if you were building Android applications, the best tool for building Android applications is Android Studio. And you would write your code in Java, right, to build Android apps. If we wanted to build iOS applications, the best tool that we would be using is Xcode. And we'll write the programming language that we would typically be using would be Swift or Objective-C. Objective-C is kind of outdated these days, so the programming language would be Swift. But Visual Studio, Android Studio, Eclipse, Xcode, and so on and so forth are all IDEs, if you will. Xamarin Studio used to be one that was also relevant. So that is just a program that's used to build programs, where we write our code and edit our code and manage our code, right? Why C#? C# can be used to build web applications. We talked about the fact that you could use Java to build Android apps, but we're going to be able to build Android apps using C# through the magic of the Xamarin platform, which we'll talk about later on. We can also use C# to build games. If you study the Unity framework, we can build Kinect games, Xbox games. You can build hardware prototypes and have a 3D printer print a camera that you build and write programs on top of it using C#. And I've got some examples using the Gadgeteer framework. We can build all kinds of applications, Windows Store apps on a Windows 10 app, operating system, so on and so forth. Next, I would recommend that you look at the tutorials on D2L. If you have a Mac and you're looking to install Visual Studio on it, which I strongly urge you to. If you have a laptop, you want to bring it to class, I would strongly recommend, if you have a Mac, install Parallels on it. Parallels is only $39.99. You can click on this link and go download the student version of it for $40 or so. So you don't have to buy a textbook for this class, you can invest in Parallels. It would allow you to install Windows on your Mac. Once you install Windows, you can install Visual Studio Community on it. So just Visual Studio Community, you can download that from this link down here, and it's free. You don't have to buy anything. If you're not comfortable with installing Windows on your Mac, so long as you've installed Parallels, I would have a pre-configured virtual machine that I bring to class, and you are welcome to download my installation of Visual Studio on it. Since it's free, you should be fine. And you have access to Windows through Microsoft's Azure subscriptions. Now you could also install Visual Studio Community if you decide to build iOS and Android apps. You could simply install Visual Studio Community for the Mac on your Mac. You don't have to install Windows first if you're going that route. I wouldn't recommend you go the Android iOS app on your Mac unless you have at least 8 gigabytes of memory on your machine. Otherwise, this is not a good option. You're going to be very frustrated. This course would not be fun for you. So if you don't have 8 gigs and you can't upgrade your machine, don't go the iOS Android app route. Now, if you have a PC, then you don't have to buy anything, right? You can simply go to this link, download Visual Studio Community for free, install it, and you're up and running. If you want to build iOS apps, you would also need access to a machine. So iOS would not work here. Not easily. It's possible, but not easily. So I'll say not suitable for iOS apps. You would need access to a Mac in addition to your PC. And if you're going to do that, why not just build it on the Mac, right? So if you're going to do Android apps on your PC, you should be fine. Unfortunately, Apple has some restrictions on how you can compile applications. iOS apps can only be built using a Mac device, and there's nothing we can do about it. Technically, you could look into Hackintoshes, but those would not be legal. So I wouldn't recommend you spend any time on that. Right? So general idea, if you have a Mac and you're going to do web, download Parallels, install Windows on it, then install Visual Studio. Once you've installed that. And there's some tutorials on D2L that you might find useful. So recap, we talked about a computer system, difference between hardware and software. We talked about programming languages, paradigms, the history of C#, some terminologies, binary code, what compilers are, what an IDE is, what the CPU does, and that type of thing. Spend some time looking at the group report that's published on D2L. For your group assignment, all you need to do is come up with the team members, 3 to 4 team members for your group. Ideally all in favor of whatever app you guys are choosing to build. So spell out the product name for your product. Define whether it's going to be a web app, iOS app, or an Android app. Give me a short description of the project. And the meat of this is going to be doing the competitive analysis. You can use something like SWOT analysis to do this, which is strengths, weaknesses, opportunities, threats. By looking at some of these categories in terms of the product that you're proposing to build, why is it innovative or unique, and 3 potential direct or indirect competitors for the product that you're looking to build. Here are some examples of previous apps that folks who have competed in our competition have previously built. So you can click on these links and follow along and see what others have built to get some ideas. All right. Otherwise, have a great rest of your week, and we will talk to you guys next week.